Thank you. First of all, Torre Velasca, the Velasca Tower is, as you said, an iconic symbol in Milan. Even if we now have a few towers and skyscrapers and chairs involved in all the towers in Milan after 2000 years, like the Porta Nuova Towers or the City Life Towers. This one was built in 56 in less than 300 days. The structure was erected at that time in less than 300 days. This is something important to understand because, as you will see, most part of the structure is exposed to the environment. And it has been after the Second World War an industrial town, Milan, and we are suffering still with the phenomenon of pollution that is not doing very well for concrete structure, especially when the durability was not a parameter in the design like in the 50s or 60s of last centuries. These concretes are porous and they were absorbing the pollution and the polluted air, so there was a lot of degradation. The new owner of the tower, an American company, Hines, decided to retrofit and renovate the tower, and this job has been completed in these days at the end of 2024. We will describe all the renovation in terms of structures and facade, where the concrete has been widely used. As an introduction, I show you the concept design that were made in the 50s from this very famous study of BBPR, and the structural engineer was Professor Danusso, who was teaching in Politecnico of Milan structures in the 60s. You can see that the original concept has been evolved, and also a steel solution was approached with the structure was originally thought because of the height of the tower at that time, and because in US at those times only steel was the material used for such a tower. You see, from the very beginning, the challenge was to have the top part of the tower that was cantilevered from the inner part, but at the end, the final solution, because of time of erection and cost, was decided to use the concrete. I think this is a challenge. Concrete was used not only for the main structure, but we will see also for all the facade. As I mentioned before, the structure is having two main cores in the center for the stairs and the elevators, and the other main structure is outside the building in the facade, and is also taking care of the change of plan happening on the 18th level, where it's also the function related to the spaces changes. The bottom of the tower has been always devoted to office, and the top of the tower, it was always devoted to residential and apartments, while the bottom part has been devoted to commercial, and the two levels of the basement have been devoted to parking spaces. The challenge structurally was to keep the loads from the top apartments part and bring those loads back into the smaller plan of the offices with these struts that are all outside the building, and a tension tie made by the slab at the 18th level, and a compressed tie that is a slab at the 15th level. This is the big structural challenge that was happening at that time. You see the shape of the columns has been a T shape that is changing with the height, giving the necessary and the needed stiffness to the tower, while also some architectural aspects like the parapet were originally conceived with structural beams to give the necessary stiffness to the borders of the plan. So it's a normal concrete structure, but with some very typical, with very untypical elements, such as the tie beam and the struts where the plan is changing area. The slabs are made with hollow clay floor in all the slabs, apart the 15th floor where we have the compression that I showed you before, and the 18th floor slab where we have the tension because of the change of the stresses. Also, for the facade, concrete material was used largely in all these particular. You see these very thin and small, not structural columns. They are only architectural elements. The prefabricated panels that have been used to border the windows, and all the other elements around the windows are all made in concrete, with concrete. You see here this prefabricated element, and you see the gravel and colored stone that are so characteristic for this facade in the original pictures in the 50s of the last century here. The methodology and the approach that has been used to retrofit the tower was, of course, to understand where the structure and the concrete was suffering from the pollution they were behaving for more than 70 years. And you see here the original picture of the beams and the columns, and you see the cracks of these beams. These beams are not with exposed concrete. We have 2 to 4 centimeters of plaster that is made with the base of concrete and with a particular pink color that is a characteristic of this tower. This plaster was completely polluted, where the water in the pore of the plaster had been damaging this plaster and had to be removed completely, while instead the concrete inside the structural content could be retrofitted. we did and performed several investigation with visual, with non-destructive test, semi-destructive test, to understand how deep the aggression had been from the pollution. You see here another original pictures of the 50s with the 18 floor slab where the ties were put with the rebars, and the shape of these ties were this outside column were pushing to diagonal struts, and therefore there were giving a lot of tension to this 18 floor slab. Here is the vertical force of the 25th to 18th floor, and then this force should go into the 15th floor column, and this of course is a big tension, horizontal tension, that is kept by the designer with these rebars that at this time they were not using post-tension rebars or special cables like in the first post-tension bridge that were built in France, for example, but they use normal rebars with plates at the very end, with this shape to allow for the other structure like the cores to go in between these tendons. The inspection was also finding a cracking pattern that was there was a little worried for the 18th floor. The 18th floor was also keeping all the HVAC systems, so was completely exposed to the outside environment, while on top of the floor there was there were the apartments that were closed, and below the offices that were closed. So this interruption of the closed environment and of the apartment offices created also a loading condition with different temperature that was causing as well the crack. So what we decided, this was also the investigation we were talking about, the width of the cracks that were not going through the whole slab width, but they were really wide. And of course, the aggression of the rivers had been starting already. Here you see the head of the ties that we show with the plates. We are very concentrated position of ties and of the head, and you see the rest of these tendons and plates had been starting, notwithstanding the 4 centimeters of plaster and the cover of this structure. The carbonation was already going on for this structure, and the durability for the plaster was really zero. Instead, for the concrete structure, some aggression had been already starting. We were not allowed, because this tower is protected by the superintendence of cultural heritage of Milan, to introduce structural elements like could have been, for example, post-tension cables that should have been seen outside the original structure, and therefore we were obliged to use a system that would allow the original structure to remain as much as possible in the same dimension as it was conceived. This system was selected with the carbon fiber system, and you see here the layout of the reinforcement of the slab, while here you can see the layout of the reinforcement in carbon of the original tendons. The rebars are inside the slab. These layers are instead on the bottom side and on the top side of the concrete slab to be in parallel to the original rebars that are kept still, but we have a huge reinforcement with the same type of layout to allow a new life cycle for the structure of this tower. You see here from some pictures how we had to deal. The plaster was removed completely from all the structures of the towers because, as I said, it was already all carbonated, and part of the plaster had started also to collapse. And you see how little is the thickness of these carbon layers, so that the final solution is allowing for the original dimension of the exposed structure and of the inside structure to remain almost the same. It is important also for the plasboard that had been put in place. It was fundamental to track all the reinforcements so that in case you had to apply a tectonical or lighting to this ceiling, you would not touch or create problems for the reinforcement that was put in place. Many testing has been performed on the intervention with carbon fibers. The control of the temperature, of course, was a key part of the intervention because, as you know, the epoxy resin has a cycle of application and a cycle of becoming hard that is related to the temperature you work with. As we will perform, of course, all the tests provided by the codes, also to guarantee that the tensile rupture and the young modulus would reach what had been studied. Another drastic and more hard intervention has had to be made for the garage. The parking you see here had been originally with the clay floor and the concrete structure in between. But the problem with this structure under the rain has been for those years of construction, the waterproofing. The waterproofing of this concrete structure was never adequate to what the concrete needs, so protection from water. And therefore, here you see the result of 7 years of work of oxygen and water, aggressing the rebars, aggressing the porous concrete that were used in the years of the 50s. Of course, it was performed also. You see here is the plan of the foot of the tower, where instead the slab were perfect, and the outside square slabs where the parking is on the basement, instead were suffering the lack of waterproofing on the top. So we checked the complete situation with the plaster detachment and the degradation that is shown in the picture before, and it was decided to completely demolish this perimeter area of the basement and to rebuild it with this type of new elements to guarantee the same type of layout that there was before, but with a new floor completely, with the result of having this ceiling that was approved by the superintendent of the cultural heritage. Now I leave also to Maxine, who was dedicated to design and supervise the work of restoration of the facade, to describe also what was going on with the facade.
So the first step for the restoration design aimed to collect all the available knowledge and studies regarding the facade, with particular focus on the degradation phenomena. Over the years, the building was subject to past remediation works. After 20 years of the building's inauguration, there were several facade elements that had deterioration signs, such as mortar detachments that were repaired. Further activities were performed in the 90s after the detachment of plaster and concrete cover at the connection between strut, I-beam, and column at the 18th floor. The most complete information regarding the state of conservation of the facades was the study conducted by the University Polytechnic of Milan, where the study aimed at characterizing the geometry, the materials, and this degradation phenomena of the opaque facade elements. The conclusion of the study reported that the finishing layer of the structural elements was carbonated through the entire thickness. Also, the elements presented cracks and significant plaster detachments. The prefabricated elements were also entirely carbonated and presented widespread detachments. Since 2011, the building is subjected to the restrictions and protected by the Superintendent of Cultural Heritage of Milan. Therefore, any intervention must be evaluated and approved by the Superintendent. The second phase for the restoration design involved inspections and testing methods in order to evaluate the current conservation state and to determine the extent of the facade intervention. The preliminary on-site inspection showed extensive crack patterns, which we can see here, plaster detachments, mortar detachments, and exposed rebars, both on the prefabricated elements and on the reinforced casting situ elements. So a new service campaign in 2020 was performed in the same areas investigated in 2008 in order to evaluate the degradation extent and the evolution of carbonation over time. On-site tests were performed using rope climbing access technicians because it had to be approved by the superintendents, and carbonation tests were performed by the Laboratory Polytechnic of Milano in order to understand the carbonation depth of the both prefabricated elements and reinforced concrete elements. In this image, you can see the before and after test of the carbonation depth, where the uncolored core represents the carbonated part, while the purple colored core represents the uncarbonated part. So the results of this campaign demonstrated how over the last 12 years, the carbonation process involved 100% of the core samples In 40% of the samples, the carbonation depth reached the concrete cover, denoting a potential depassivation of the reinforcement bars. Over time, the reduction in diameter of the reinforcement bars accompanied by the chemical process of corrosion, can cause a significant loss of the load-bearing capacity of the structures. This campaign also established that there was no correlation between the facade elevation and the degradation extent. It was therefore necessary to intervene on all the opaque facade elements to stop the carbonation and corrosion processes and to guarantee a new service life for the building. The restoration and renovation of the reinforced concrete structural elements consisted in the plaster thickness detection using stainless steel nails to guarantee the authentic reconstruction of the original building geometry, since the tower is under protection as a historic building. The total removal of the existing plaster, the hydrosterification, which is the application of a high water pressure in order to remove the incoherent parts of the reinforced concrete, the passivation of exposed rebars, and the reconstruction of the concrete cover, and the final layer, applying a bonding layer with fiber mortar and a new plaster finishing that is 15 millimeter thick. A subsequent air abrasion was performed on all the surfaces in order to enhance the aggregates and the texture of the plaster. And finally, a water repellent treatment was applied. For the prefabricated elements, the design involved the following activities, which are sandblasting and manual demolition in order to remove the incoherent parts and remove the dirt, rebar passivation of the exposed rebars and reconstruction of the demolished parts with mortar, that pictorial integration of the reconstructed parts, as you can see here, and water repellent treatment. The creation of a plaster that respected the original color of the building was the most delicate phase. The mixed design of the plaster was defined in collaboration with Mapei, leading to the creation of a new plaster binder called Velasca binder, able to guarantee the required durability. Various samples were prepared on site to compare the new plaster to the existing one, because we needed to obtain the approval of the superintendent in order to proceed with the selected color. So they had the final say on the material and the aesthetic result of the plaster, selecting sample G, that is realized using 30% of plaster binder and 70% of marble stick aggregates such as red Verona marble chip, coral pink, Botticina white, and ebony black. These aggregates were measured and weighed on site with a calculated mixture of marble chips with different grain sizes ranging between 0 and 6 millimeters. Also, the restoration of the prefabricated panel and pillars was subject to the superintendent that chose the panel F that has only one water repellent coating. In order to guarantee the durability of the entire mortar cycle applied on the structural elements, both laboratory and on-site tests were performed. During the design phase, we performed adhesion tests in order to provide the certification for the applied mortar cycle that can resist to severe exposure conditions over time. During the construction, more than 28 pull-off tests were performed in correspondence of the different layers of the mortar cycle to measure the adhesion of the mortar to the support and to ensure the correct installation of each product. Karsten tests were performed as well in order to measure the amount of water absorption by each element, both prefabricated and reinforced concrete. And in all cases, we ensured that the correct application of the water repellent treatment was performed. Finally, a maintenance plan was developed both for the structures and for the facades, outlining the scheduled tasks and activities to perform ordinary and extraordinary repairs. Furthermore, tests are scheduled on the facade elements performed by access rope technicians, such as pull-out tests on the reinforced concrete elements every 10 years in order to monitor the carbonation phenomenon of the load-bearing structures, and non-destructive tests, such as Karsten tests, are programmed every 2 years in order to evaluate the effectiveness of the water repellent treatment finishing layer over time.
Thank you.
Thank you.